Okay, let's get started with the second part of the lecture. We're going to switch to branch prediction, which we have briefly covered in an earlier lecture when we discussed pipelining and dependencies and control dependence as a form of data, as a special form of data dependence. Now we're going to go into branch prediction in a little bit more deeply, because it's been a fascinating topic, and it's been one of the enablers of why these pipeline machines have been extremely successful, because branch prediction and good branch prediction algorithms that have been developed over the course of decades have enabled people to keep the pipeline full and moving as much as possible. For this, I would recommend reading the Combining Branch Predictors technical report, which has been quite influential in the field. And it's a very nicely written report describing some branch predictors that we're going to talk about. But this topic is also covered in the microarchitecture of superscalar processors reading that you're doing. Okay, so this is what we covered. We have started other execution paradigms, and just now we have covered data flow and superscalar execution. We're going to cover more paradigms, but it's important to cover control dependence handling, branch prediction before we move on, because branch prediction is extremely instrumental for many things we have seen, or control dependence handling is very instrumental to things we have seen. And it's going to be very instrumental for other things we're going to see also. So we're going to talk about briefly branch prediction when we talk about VLIW, decoupled access execute, SIMD processing. We're going to talk how to handle branches over there. And even systolic arrays require hand decision making, basically. So keep that in mind. Control dependencies are quite fundamental in the end. They exist in data flow machines also, as we have discussed, except they are converted to data dependencies. But if you can execute them faster, then they could enable you to be faster in a data flow machine. But maybe they're not as disruptive to a data flow machine. Okay, so control dependence, remember the slide, we covered this also briefly. Well, we covered it actually. Basically, the basic question we're trying to answer is, what should the fetch PC be in the next cycle in a pipeline processor? And the obvious answer is the address of the next instruction to be fetched, right? But how do you know that? Because all instructions are actually control dependent on previous ones because of sequential execution, because of dependence on the program counter, right? Every instruction changes the program counter. Now, some of them trivially change the program counter. They increment the program counter, or change the program counter by the size of the instruction. If you don't have fixed size instructions, that becomes a problem as well in branch prediction or control dependence handling, if you don't have fixed size instructions. But the real problem happens when you have control flow changing, sequence changing instructions like branches, conditional branches. So if the fetched instruction is not a control flow instruction, then the next fetch PC is the address of the next sequential instruction. And if it's PC plus 4, for example, like in MIPS and many other ISAs, then you can safely increment the PC. And that's what we have done so far, right? Incremented the PC and assume that it's good. If it's not a good decision or good prediction, let's say, then you figure that out when the branch is resolved and you flush the pipeline. And we have seen that already. Of course, this is easy to do. If you know the size of the fetched instruction, you increment the program counter by the size of the fetched instruction without having to decode it. But if you do not know the size of the fetched instruction, which happens in variable length instruction set ISAs, x86 is one example where instructions can range anywhere from 1 byte to 16 bytes, 17 bytes, I think right now, actually. Don't quote me on it, but they've also been changing the ISA, evolving it over time. But certainly anywhere between 1 to 15 plus bytes, let's say. And you determine the size of the instruction after you decode the instruction. Basically, you don't know the size of the instruction before you decode it, which means that the fetch stage, you don't know what to fetch, basically. You can guess, of course, the size of the instruction. And that's what a lot of x86 processors actually do today. They guess the size of the instruction. Okay, so this becomes a problem even when the control flow, the fetched instruction is not a control flow instruction, if your ISA is not nice, so that you don't know, such that you don't know the size of your instruction. But of course, it's a bigger problem if the instruction that's fetched is a control flow instruction, because you haven't even executed the instruction. You don't know whether it will be a taken branch, if it's a conditional branch. And how do you determine the next fetch PC? You need the next fetch PC in the next cycle immediately, right? It's not like you have a lot of time to determine it. You need it at the end of the cycle so that you can have the full next cycle, so that you can access the instruction memory with the next fetch PC. I mean, we don't even know whether the fetched instruction is a control flow instruction. So we cannot even distinguish between those two cases because we have not decoded the instruction yet. The instruction is being fetched at the moment in the fetch stage. So a control dependence, that's why it's so disruptive to a pipeline processor, because at the beginning of the pipeline, it immediately poses you a problem. What are you going to fetch next? And we're going to handle this basically in the next couple of today and in the next lecture. And it's important to remember that there are many branch types in an ISA, and these are some examples. There are conditional branches, unconditional branches, calls, returns, and indirect branches. And an ISA actually have many more combinations, if you will. And different branch types can be handled differently, just like we designed different data path elements to handle different branches. The J instruction, MIPS jump instruction was different from the BEQ, for example, branch equal. A branch equal is a conditional branch. Direction at fetch time is unknown. And that's a problem, basically. You don't know whether you should be taken or you should be going to the taken path or not taken path. And there are two possible next fetch addresses. And the next fetch address is resolved at the execution stage. So this is register dependent usually, right? Depending on the addressing mode, of course, but the tough ones are register dependent. And these are the ones that we're going to deal with a lot in this lecture. Other branches also cause problems, like unconditional branches are always taken. There's only one possible target address, as you know, and you can resolve the fetch address at the decode stage early, as we have discussed earlier, with some trade-offs. But you still need to have a bubble in the fetch stage, right? Because you don't know the target address until you decode the instruction. So this leads to a bubble. Call instructions are similar. They're always taken, and you can resolve them at decode, but again, they can lead to a bubble. Return instructions are also similar, except the number of possible fetch addresses or returns can be many, because you may have many different call sites calling the same function, right, in a program. And you need to be able to return to the real callee or real caller, basically. That's why we save the address of the instruction after the call onto the stack, such that the return instruction can pop it and return back to it by jumping to that register, right? Jumping to the address in that register. So you can actually optimize calls and returns. If your program is nice, you can push the address after the call onto a hardware structure called the return address stack. And whenever you see a return instruction, you can pop the target address in the hardware structure and use that as your next fetch PC, right? Now, if you have the stack, and the stack is nice, meaning calls and returns are always balanced in your program. The programmer was nice such that they always call, and then return, and the nesting level was always correct, etc. Then this hardware structure called return address stack can be extremely useful and extremely accurate in real processors, actually. Real processors use these call return stacks or return address stacks. It's also called CRS, call return stack. But basic idea is whenever you fetch a call, execute a call instruction, you push the target address, push the address of the next instruction on the stack. And then whenever you execute the return instruction, or whenever you fetch the return instruction, you pop it from the stack. Of course, this needs to be done in order, in program order. I'm not going to get into how to do that. I have some backup slides, which we probably are not going to cover even in the next lecture. But I wanted to give you this idea that calls and returns can be handled more easily if you assume that a program does call and then return, and there's always a matching return, right? Okay, indirect branches are tough. They're always taken, but they have many possible next fetch addresses. Basically, indirect branches jumping to a location specified by a register, right? And that location could be anything, right? This could be useful for implementing virtual function calls, for example. I'm not going to go into the details of it unless we have time at the end of the next lecture. But these are actually tough branches to predict, because there could be many possible target addresses, and you don't know the target address until execution. So indirect branches and conditional branches are the most difficult branches in a machine in general. Usually in ISAs, you don't have conditional indirect branches. If you had a combination of conditional and indirect, then it's not always taken, and even the direction would be unknown over here, right? But usually you don't have that in existing ISAs that we have. But we're going to tackle the conditional branches mainly in this lecture. And if we have time at the end of next lecture, we may cover some of these other ones. I've already given you the basic idea of a return address stack, which you can think about a little bit. But this is to show you that different branch types can be handled differently, and they have to be handled differently. Otherwise, if you try to handle them using the same mechanism in your pipeline, then you're probably penalizing yourself, because the same mechanism dictates that you handle the worst case again, and worst case could be indirect or conditional indirect together if you have that. But you can easily handle unconditional branches, as I said, and you can relatively easily handle call and return instructions as well. Okay, so basically, it's critical to keep the pipeline full with the correct sequence of dynamic instructions. And this is no news to you. And there are multiple potential solutions if the instruction is a control flow instruction. You can stall the pipeline until you know the next fetch address. Bad idea. We've discussed this briefly. I'm going to discuss very briefly again and dismiss it. You can guess the next fetch address, branch prediction. And we've done it actually, as we discussed earlier. We've predicted the branch as not taken in our earlier lectures about pipelining. We're going to do better in this lecture, basically. Can we do better than not taken prediction? But we're going to also cover some basics of branch prediction before we get there. You can employ delayed branching, branch delay slot, which MIPS employs. I'm going to talk about this after in the next lecture sometime, hopefully. But this is in general a bad idea, because basically, this basically says that branch takes effect after n cycles or after n instructions. And it's the compiler's job or the programmer's job to fill those n cycles with independent instructions. Now you're basically putting a lot of burden on the programmer and the compiler. And worse yet, somebody needs to decide this n. How many cycles? Now that becomes extremely problematic, because branch misprediction penalty is really a function of the pipeline depth. And pipeline is fundamentally a function of microarchitecture. We don't want to expose it to the ISA. But if you have something like a branch delay slot, if you change the semantics of the branch instruction such that it requires information from the microarchitecture, now what you're doing in the ISA is not very clean, if you will. And this has caused a lot of problems. Actually, MIPS, because of its philosophy, it employed delayed branching. It has a single cycle branch delay slot. It assumes that the branch will be resolved in the second stage of the pipeline, which is not a good assumption, clearly, in existing pipelines, especially out of order execution pipelines. So now people are stuck with it, basically. So it doesn't buy you anything. It just gives you a lot of hurdle in code generation and also implementation in hardware as well. Do something else, fine-grained multi-threading. We already covered this in its own part of a lecture related to pipelining, as you remember. Certainly, fine-grained multi-threading gets rid of the control flow dependencies within a thread. Because by fetching instructions across different threads, so you don't need to predict branches at all, because you're not filling the pipeline with instructions from the same thread anyway. And clearly this is nice, but we already covered the trade-offs. You can eliminate control flow instructions using multiple methods. I'm hopefully going to cover that briefly today, but if time permits, we're going to talk about that next week also. This is called predicate execution. This is basically the idea of converting control flow instructions to data dependencies. And you can do that, right? You know the model of data flow right now. Data flow doesn't have branches. Data flow has these nodes that basically make decision-making nodes, or called conditional nodes in lecture 11. So clearly you can convert branches into data flow nodes. And that's essentially this idea over here, predicate execution. The compiler does it. Hardware can potentially do it with additional cost. And if you do that, you can eliminate the problem, but now you turn the problem to a data dependency problem, right? And we'll hopefully cover this briefly. This is an idea that was employed in some ISAs, like IA64 and ARM. And the last idea is fetch from, okay, whenever you get to a branch, you get to a fork, take both paths, right? Of course, this requires you to have more hardware, and you to know the addresses of both possible paths. Assume that you figure that out, and we're going to see how to figure that out potentially. This is called multipath execution. This is a hardware intensive solution, and potentially it could be useful if you do it as a last resort, if your branch prediction is not good, for example, etc. And we will briefly talk about it maybe at the end of next lecture. But I wanted to give you the high level idea of these 6 different potential solutions for handling control dependencies in general and branches in particular. Okay, now let's take a look at the stall the pipeline solution and dismiss it quickly. We've already seen kind of last time, but basically you have a branch instruction. Do you want to stall the fetch until next PC is known? Is that a good idea? Not a good idea. Even if you have an unconditional branch instruction, which gets resolved in the decode stage, you cannot fetch the next instruction, right? Basically, that becomes a bubble. the branch resolves. Basically, it's a non-control flow instruction, even non-control flow instruction. Basically, we're looking at. You're not doing any prediction basically, but unconditional branch instructions also you can assume that they're being resolved in the decode stage, right? Basically, you at least need to decode the instruction. And if it's a non-control flow instruction, you know that the next PC should be PC plus 4, but you can also only fetch it in the next cycle, right? And that's true for unconditional branch instruction. You calculate the next PC in this decode stage, and then feed it to the program counter, and you can only fetch the next instruction in the next cycle. Basically, for non-control flow and unconditional branch instructions, if you wait until the next PC is truly known, you're wasting half of your pipeline throughput, because only every other cycle you're fetching a useful instruction. So clearly, this is a very bad idea. You should do at least some prediction. And the safest prediction, as we discussed, easiest prediction, not necessarily the safest prediction. Easiest prediction is predict that next PC will be the sequential PC after the previous instruction, PC plus 4, basically. And we have seen it also. So that's why stalling is a bad idea in general. Okay, so we've seen do something else. I'm not going to go through that, so I will eliminate that solution. If you're interested, you can look at the pipelining lecture again, study it again. But fine-grained multithreading is a very powerful idea, clearly. This is how GPUs ensure that they don't need to do branch prediction within a thread. Right? Now we're going to focus on the solution of guessing the next fetch address. We already know the solution, but now we're going to design better algorithms. And this has fascinated people over the course of 40 years or so. And it's really amazing what people have built into branch prediction hardware. There's, of course, more work to be done. But today we're getting into accuracies like 96%, 98%, in some cases 99% accuracy in terms of the prediction of the branch. But we will see that that may not be enough if you keep building bigger and bigger and wider machines. Okay, let's take a look at this problem basically. So the problem is control flow instructions, branches are frequent. They could be anywhere between 15 to 20%, 25% of all instructions in general purpose programs. The problem is next fetch address after control flow instruction is not determined after n cycles in a pipeline processor. And n cycle is really the branch misprediction penalty or minimum branch resolution latency, essentially. I say minimum over here because in an out of order machine, this could be longer, right? If the branches depend on a long latency load operation, then it may actually wait for hundreds of cycles, maybe thousands of cycles potentially in the machine without being resolved. Okay, keep that in mind. In out of order execution, whenever you have dependencies to long latency instructions, even in order execution, this happens, of course, but out of order execution amplifies the problem because you have many more instructions in the machine. Then you may actually be waiting in the machine for a long time for a branch that is not resolved yet. So, okay, if we're fetching W instructions per cycle, in other words, if the pipeline is W wide, this is really the superscalar width. We're assuming a superscalar machine. A branch misprediction leads to n times W wasted instruction slots because you're waiting for n cycles at least, and each cycle you are supposed to fetch W instructions. You're wasting those opportunities. N times W instruction slots are wasted, and this is really the branch misprediction penalty in a superscalar machine. In a scalar machine, it's n cycles minimum. In a superscalar machines, it's n times W wasted instruction slots at minimum. Now, let's take a look at the importance of the branch problem by doing an exercise. Assume that we have 20 pipeline stages, which is reasonable in today's standards. N is 20, basically. Branches resolved after 20 cycles. And W is 5. We're doing 5 wide fetch. I picked that number so that we can ease the calculations a little bit. Assume 1 out of 5 instructions is a branch. Okay. And assume each 5 instruction block ends with a branch regularly. How long does it take to fetch 500 instructions? So there are multiple ways of approaching this problem. I will let you find your own approach. In general, that's my approach. It's best for you to find your own approach to approach the problems. But let me give you how I would approach this problem, basically. So I'm asking, of course, the question is not complete yet. How long does it take to fetch 500 instructions? I cannot just ask you that. I should give you the accuracy of the branch prediction, right? If the branch prediction is 100% accurate. Okay. So if the branch prediction is 100% accurate, I have 500 instructions. I don't care about the branch, right? Because it's always accurate branch prediction. I don't have any delay, if you will. So basically, I'm fetching 5 instructions per cycle, and I have 500 instructions, meaning that I should be able to fetch all of them in 100 cycles, because all instructions that I fetch are on the correct path, right? Okay, so this is easy, hopefully. I have 5 instructions per cycle. Branches don't impose any penalty because I'm 100% accurate. And I'm fetching 5 instructions per cycle. So I have 500 divided by 5, 100 cycles. Okay, so there's no wasted work. IPC is perfectly 5, assuming no data dependencies, of course. I'm assuming that also. That was not written over here. Okay, so this is great. Now let's go to 99% accuracy. So basically, this says that I have 1 out of 100 branches mispredicted. I'm fetching 500 instructions. 1 out of 5 instructions is a branch. So I have 100 branches here, which means that I have 1 branch mispredicted. Among those 500 instructions, I have 1 misprediction. Okay. So how do I approach the problem? Basically, I still need to fetch all of the correct path instructions. I cannot get away from that. In the end, I have to fetch from the correct path. So I need to spend 100 cycles fetching the correct path instructions. I have one branch mispredicted. For that 1 mispredicted branch, I spent 20 cycles on the wrong path. Okay. So basically, I waste those 20 cycles, right? So my program now takes 120 cycles to fetch. So that's the calculation. So hopefully that's clear because only 1 branch is mispredicted, right? Okay. So basically, you fetch 20% extra instructions in this case because remember that 20 cycles you're spending on the wrong path, 100 cycles you're spending on the correct path. So your IPC becomes, fetch IPC at least, 500 divided by 120. Okay, let's go to 90% accuracy. 99% is a lot, actually, very good. If you go to 90%, the problem becomes worse. So 90% means 10 of those branches is mispredicted. So I have 100 branches, 90% accuracy, meaning 10% misprediction rate. 10 of those branches mispredicted. I still need to fetch 500 instructions. To be able to fetch 500 instructions, I need to spend 100 cycles on the correct path. Now I'm spending 200 cycles on the wrong path. Why? Because 10 branches are mispredicted, and each branch leads to 20 cycle wasted time on the wrong path. So now I'm spending 300 cycles to fetch 500 instructions. Now quickly it became bad, right? And I've fetched 200% extra instructions. You can see from the ratio over here, 100 cycles are spent on the correct path, 200 cycles are on the wrong path. Now my fetch IPC is 500 divided 300, 1.6 bar, which is much worse, which is 3 times worse than the perfect IPC with perfect branch prediction. Okay, now you can go to the exercise. If you go to 60%, you have a terrible machine because you're spending a lot of your time on the wrong path, most of your time on the wrong path, as you can see, right? Because each branch causes a 20 cycle delay, and you have 40 of those, even though your accuracy is 60%, better than random luck, right? So this is the importance of the branch problem. You have a wide and deep pipeline. You're wasting a lot of cycles on the wrong path, even if you're 60% accurate, even if you're 90% accurate. 99% is not terrible, as you can see, but you're still wasting 20% extra instructions, right? So that's the importance of the branch problem. And keep this in mind. We're going to do this exercise again after building some branch predictors. And it's going to be important to look at that exercise again. Okay, I would like you to convince yourself that this is correct. You can do this exercise on your own, but it's a very important exercise to understand the importance of feeding the pipeline with correct instructions. Okay, now let's go into branch prediction. Clearly, you know the basic idea, right? Instead of stalling the fetch, we guess the next instruction to fetch, right? So stall fetch, essentially, so we have this branch instruction, blue instruction, and this is a short pipeline, not a deep pipeline, as you can see. Stall fetch is a bad idea, as we discussed, because if you do that, it takes a long time to refill the pipeline. Branch prediction, if you guess correctly, you keep filling the pipeline nicely. And you can do this animation on your own. We're past beyond this point, actually, at this point, because we already know that branch prediction is a good idea. But if you do this, you can see that we immediately gain, even in the shallow pipeline, 1, 2, 3, 4, 5 stages, right? We immediately gain 33% performance improvement, right? Okay, but of course, if you mispredict, then you need to flush the pipeline. Okay, and we know that also. Okay, So what is the branch? Let's talk about branch prediction algorithms. What are different algorithms to do? And we've already seen this. Always guess next PC is equal to PC plus 4. Always predict the next sequential instruction is the next to be executed. This is a form of next fetch address prediction and branch prediction. It's called the not taken prediction. Basically, implicitly, you're predicting that the branch will be not taken. Okay. How can you make this more effective? So assume that actually this is not very effective. It turns out its prediction accuracy is 30 to 40% if you're lucky. And 30 to 40% is terrible, as we discussed, right? If you have the assumptions that we made earlier, you'd be fetching actually lots and lots more instructions into the pipeline and wasting a lot of cycles. But there are methods to make this more effective. Basically, the compiler, for example, can maximize the chances that the next sequential instruction is the next instruction to be executed, potentially, right? So software, compiler or the programmer, can somehow lay out the control flow graph such that the likely next instruction is on the not taken path of a branch. And this is actually a cool idea. It's called profile guided code positioning. It was developed by Pettis and Hansen in PLDI 1990, if you're really interested in looking at it. And many existing compilers actually do this today. Let me do something over here. Maybe I will share my screen on my iPad so that we can go over this very quickly. Start broadcast. Okay, we're seeing some screen over here. Now let's go to good notes over here. Okay, so basically, you have this code. Let's say block A. Okay, yeah, let's do this. You have, let's say, if some condition, you execute block B, else you execute block C, and otherwise you go to block D, and then you have block A over here. Okay, so this is the taken path, right, in your code, and this is the not taken path. Now, if your code is somehow laid out such that you have A, B, and then D, there's an unconditional jump over here. This is not good for not taken prediction, right? Why? Because to transition from A to B, the branch needs to be taken. But your processor is predicting not taken. So whenever you're transitioning from A to B, this is the block B, block A, block C, block D over here. And the code is laid out sequentially like this, sequential layout. Let me do it this way. And the layout is done by the compiler or the programmer. This is a bad layout for a not taken prediction, because transition from this sequential block to this sequential block is not sequential. You have to have the branch to be okay. Maybe I should have said something else over here also. Basically, I should have said something like C is over here, and okay. So okay, let me reconstruct this example. Sorry about that. But basically, let me do the control flow graph that will make this more easy. You have the A, B, C, and then the control flow graph looks like this over here, right? And the branch is taken if you go from A to B, and it's not taken if you go this way. Okay. Now let me actually draw this differently so that we're more aligned with this prediction method. So I'm going to make the C. So my layout is ACD. Okay. Now ACD is nice layout when the branch is not taken, right? If your prediction is not taken, then you're executing like this in the control flow graph, right? ACD. And your sequential instructions are ACD. You're always predicting PC equals PC plus 4, and you're always correct over here. And C is somewhere else, B is somewhere else in this case. Now, this works very well if this path is the frequently taken path. That's the important information that I was missing earlier. Basically, let's assume that A transitions to C 99.99% of the time, meaning the branch is not taken 99.999% of the time. That's good. Then this layout is great. But if you have this layout, and if the branch is taken frequently, like taken 99.99% of the time, then this layout is terrible, right? Because you're not going from A to C most of the time. In fact, you're going from A to C only 0.01% of the time. Most of the time, you need to go from A to B. But your code layout is such that that's not the case. So your prediction is almost always incorrect, right? So what does the compiler do? If the compiler has this information about the control flow graph and the taken frequencies of the branches, it can lay out the code in the memory such that the taken path or the frequently executed path becomes a not taken path, right? That's the idea over here. So basically, if the compiler figures that 99.99% the branch is taken, it lays out the code such that B is here and C is here, and it's somehow does the switching such that the branch works correctly. Okay, that's the idea. Okay, so basically, the idea is to profile the code. Let me actually fix it over here so that you will see what the compiler does. So basically, the compiler figures out which path is the frequently executed path and lays out the graph, lays out the code in the memory such that the frequently executed path is the not taken path. In this case, frequently executed path is I should use another color perhaps, ABD, and you need to put B over here, and C needs to go somewhere else, and you do an unconditional jump to C from this point. And I didn't put all the things over here, and this became a little messy, but that's the idea basically. Make your frequently executed path the not taken path. Okay, and the compiler it can do it clearly, right? So let's go back to this. And this way, the effectiveness of a not taken branch prediction becomes much better, assuming the compiler can figure out the probabilities of transitioning between different control flow blocks, right? That requires profiling. If you remember one of the lectures earlier, we said compiler can get information about potential dynamic direction of the branches by profiling the code. And it requires a profile input set to be representative of the real input set. And if it's not representative, the compiler may lay out the code in one way, assuming that the frequently executed path is going to be A to B. But in real executions, if the frequently executed path goes from A to C, the compiler was wrong. And as a result, your branch prediction accuracy becomes very bad, right? So this requires the software to lay out with some information, but the software's information may not be representative. So in many cases, this works nicely if your input set is representative and branches are biased. So this doesn't work, of course, if in the earlier example that I showed you, the branch is taken 50% of the time and not taken 50% of the time. Then you don't have a frequently executed path, right? You cannot maximize the chances that the next sequential instruction is the next instruction to be executed because both paths are well balanced, right? Okay, so keep this in mind. We may get back to this actually later on. But it's a powerful idea when branches are biased, and also a compiler can lay out the code and figure out the bias of the branches. Okay, you can also do this purely in hardware. I'm not going to discuss this idea right now, but hardware can do something similar. Basically, profile dynamically in hardware, annotating the instructions, keeping information about them, etc. Requires hardware cost, of course. And it can cache traces of executed instructions. So this is also a powerful idea. It was employed in Intel Pentium 4, for example. It's the trace cache idea. And if you do it well, it can work nicely. But basically, let me actually go back to the screen sharing. If I can do this, I'll stop share. Unfortunately, I have to stop share. I don't know why. Start broadcast. Let's see if it's working. Okay, it's kind of working. I'm going to use the same example that I used earlier over here. Yeah, basically, the hardware dynamically figures out, because it executes the instructions like this, ABD, 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 it keeps executing ABD. If it keeps enough information about which direction branches went, the hardware can actually cache the directions of the branches. In fact, cache all of the instructions in ABD, these blocks over here, right? Code blocks. And this is called the idea of a trace cache in Intel Pentium 4. It's a powerful idea that actually can feed the pipeline nicely. Okay, I'll stop sharing and go back over here. Okay. No, somehow I cannot go back. Okay, share screen again. Okay, if you're interested, you can read the trace cache ideas. Okay, how else can you make next PC equals PC plus 4 more effective? If you're always predicting not taken. Well, in general, actually, how else can you make pipelines more effective? Getting rid of control flow instructions helps. This is not making just the not taken prediction more effective, but taking any pipeline more effective. If you can get rid of the control flow instructions or minimize their occurrence, that's great. So how do you do that? First of all, you can combine predicates. For example, if you're testing 10 different conditions, and if you have 10 different branches branching on these different conditions, well, why don't you combine those conditions and do a single branch? That way you get rid of 10 branches, reduce it to only a single branch, and convert everything else to data dependencies. So this is called the idea of predicate combining. You test only once, you eliminate a lot of branches, and the probability of your pipeline getting flushed because of next PC equals next PC plus 4 reduces. Of course, data dependencies may cause a problem, but that may be easier to handle potentially, right? Okay, so this is one way, and this is software way, right? A compiler can actually produce one branch for a single combined predicate. If you're testing A, if A equals to 0 and B equals to 5 and C greater than 4, instead of having one branch for each, you have a combined predicate and a single branch. Okay, the second idea is what we briefly discussed, converting control dependence into data dependencies, predicate execution. In other words, if conversion. Again, I'm not going to go through this in this lecture, but convert the control dependence into data dependency, just like in a data flow machine. So this is another example of a data flow machine influencing control flow machines by getting rid of the control flow as much as possible, at least control flow changing instructions, I should say. Okay, so always PC plus 4, we're familiar with it. I'm not going to talk more about it basically, but instruction, branch condition, and target are evaluated in the ALU. And essentially, when a branch resolves, if the target address is not matching PC plus 4, or if the branch is taken and you predicted not taken, then you flush the wrong path instructions. So we discussed that you actually have a two instruction bubble in your pipeline. Okay, of course, this depends on how deep and wide your pipeline is. As we also discussed, this is the simple pipeline that we're building on earlier. So let's do some performance analysis. Very simple. Correct guess, no penalty. Incorrect guess, 2 bubbles. Let's assume that our correct guess is 86% of the time. And assume that we don't have data dependency related stalls. 20% instructions are control flow instructions. 70% of control flow instructions are taken. Now, the cycles per instruction that we get in this very simple analysis, which I'm not going to go into a lot, is this. Essentially, normally, you don't have any penalty, 1 cycle per instruction. No data dependency related stalls. This is a simple pipeline again. But 14% of the time, you get 2 cycle additional bubble. Right, so your CPI becomes 1.28 as opposed to 1 in the simple pipeline. We've already seen the big downside of branches, so that's why I'm not going to spend a lot of time on this. But I would like to point out 2 things over here. One is the probability of a wrong guess. That's the branch prediction accuracy or branch misprediction rate, let's say. And the other is the penalty of a wrong guess, if you will. So you can actually optimize for both. Let's take a look at the penalty for a wrong guess. We can reduce either of the 2 penalty terms. And we already discussed the penalty for a wrong guess, basically. Reduce the branch misprediction penalty. So there are 2 ways we can make branches less costly. Make branch prediction better, increase our accuracy in the guess, or reduce the branch misprediction penalty. And we've already seen ways of reducing the branch misprediction penalty, right? If you remember a pipeline, we want to resolve the branch condition and target address early, as opposed to resolving it here. We resolved it here. But if you can resolve it here, that's even better potentially, right? And that was the idea over here. We basically moved the branch condition and target address resolution early to the register file stage. And if you do that, then you basically lose 1 instruction whenever you flush the pipeline, which is the instruction over here. And your CPI becomes 1.14 in this cooked up example. But this could lengthen your clock cycle time, as we have discussed earlier. You need to do register file read, comparison, and then also control the muxes and the target address calculation, which is probably not on the critical path because this may be your critical path. But basically, this may or may not be a good idea. And we already discussed under which conditions this could be a good idea. If it reduces cycle per instruction much more than it lengthens the critical path, then sure, it could be a good idea. But usually this tends to be dangerous, especially if you put it on a critical path, close to critical path logic. Okay, so let's do a little bit more enhanced branch prediction now. So ideally, I mean, in general, when you design a good machine, you should, of course, always try to reduce the branch misprediction penalty as much as possible but you should always be careful. In deep pipeline machines, it's hard to reduce it beyond some point. That's why we have branch misprediction penalties that are greater than 11 cycles, 15 cycles, etc. Today. Okay, so now let's go into branch prediction in a little bit more detail. Basically, the idea is to predict the next fetch address to be used in the next cycle. This actually requires 3 things to be predicted at the fetch stage. You need to predict whether the fetch instruction is a branch. You need to predict the branch direction, especially important for conditional branches, of course. And you need to predict the branch target address if the branch is taken. So we need different structures for this. So let's take a look at branch target address. So how do we get the branch target address immediately in the fetch stage? And then we're going to look at whether the fetch instruction is a branch, and then we're going to look at the branch direction a lot in the later part of the lecture and next time. So basically, the key observation is that target address remains the same for a conditional direct branch across dynamic instances, because target address is calculated as PC plus offset. Since PC of an instruction doesn't change, PC plus offset doesn't change. Once you calculate the target address, you can put it into a structure and remember it. That's the idea. Basically, the idea is to store the target address from a previous instance of a branch, execution of a branch, and access it by indexing it with the program counter. This is called the branch target buffer or branch target address cache. It's employed in all processors that use branch prediction. And this way, you can get the target address immediately in the fetch stage. So let's take a look at it. This is the fetch stage with BTB and direction prediction. So basically, you have the program counter. I don't show the instruction cache over here. While you're accessing the instruction cache or instruction memory with the program counter so that you can fetch the instruction, you're also accessing 2 other structures using the address of the current branch, which is the program counter. You access the cache of target addresses and also the direction predictor. We're going to study the direction predictor later. But if you actually get a target address, if you actually hit in the structure, meaning the cache of target addresses says, oh, I have something for that program counter. I've executed that program counter before, and I've calculated the target address, and I've inserted it here. And now I can give it to you immediately. And here it is. So I'm a hit. It's this access hits in my structure. Then you can use a target address of the branch. Direction predictor tells you what to use. Basically, if the direction predictor says taken, and if a target address for this program counter exists in the BTB, branch target buffer, then the next fetch address is really the target address coming from the branch target buffer. If the direction predictor says not taken, or if it's not a hit, then we fall back to PC plus 4, essentially, as the next fetch address. I say instruction size to be general here, but in MIPS, it's PC plus 4. So now this is a more complete fetch engine. Of course, concurrently, you're also accessing the instruction memory or instruction cache over here. So all of this is happening concurrently with instruction cache address. And at the end of this, next fetch address gets lashed to the program counter. In one cycle, you need to do all of this. So now we know how to recognize a taken branch, right? Actually, how to recognize a branch. If a program counter hits in this BTB, then you have previously executed that branch and inserted a target address for it inside the branch target buffer, then that program counter must be a branch. If it misses in the BTB, then you don't know. You have not executed this branch, so you didn't insert a target address to the BTB. As a result, this is probably not a branch or a branch that you've not seen before. So predicted not taken. But next time, well, predicted not taken because it's not a hit. Next time, you may actually predict it taken depending on your direction predictor. So we're going to study the direction predictor in much more detail soon. So a more sophisticated branch direction prediction actually looks like this. This part is fine. But basically, we're going to see things like you're going to use the program counter and the global branch history, meaning which direction earlier branches went. And we're going to use that to index the direction predictor. And the direction predictor will tell us whether the branch should be predicted taken or not taken. So we're going to use more context information. And we're going to see why this makes sense. Okay. So let's recap this. We require 3 things to be predicted at the fetch stage: branch target address, which can be accomplished using a BTB. We can remember the target address computed last time the branch was executed. First can be accomplished using a BTB also, whether the fetch instruction is a branch. If the BTB provides a target address for the program counter, then it must be a branch, obviously, because you should not insert target addresses for program counters that are not branches into the BTB. That's not the function of a BTB. And Or basically, we can store branch metadata bits in the instruction cache or memory and partially decoding the instruction and storing it in the I cache. I'm not going to go into this approach, but some processors actually take this approach also. That leaves us with the conditional branch direction, which is the hardest part. How do we predict the direction? So we're going to cover a bunch of different techniques. Basically, we're going to start with simple ones. These are the simple ones. We're going to talk about compile time or static direction prediction schemes. Always not taken, always taken are actually somewhat static schemes because you don't need to make a decision dynamically. Backward taken, forward not taken, we're going to cover that. Profile based, we're going to cover that. And we're going to also go into runtime prediction, which is going to be much more dynamic. And we're going to make it even more enhanced. Basically, we're going to enhance the compile time technique by program analysis. And we're going to enhance the runtime technique by actually adding more history and adding more different algorithms, as well as combining different algorithms by making things hybrid. So it's going to be fun. And a lot of people actually developed very innovative and creative algorithms to do the prediction. Let's cover some of the basic ones. We already covered the always not taken one. So advanced is clearly simple to implement. There's no need for BTB, no direction prediction, but low accuracy, as we discussed. You could improve the accuracy by laying out the code or eliminating branches, but that turns out to be hard. So basically, compiler can lay out the code such that the likely path, frequently executed path, is a not taken path. This could lead to more effective prediction, but there are downsides to it, as we have discussed earlier. Always taken, you need a BTB for this. Basically, whenever you see a branch, and if you have a BTB hit, you always predict it taken. No direction prediction needed. BTB is enough. It gives you better accuracy, 60 to 7%. Why? Because most of the branches are taken. I mentioned this last time, actually, or when we covered pipelining a little bit, because most of the branches are loop branches, and usually loops are iterating. Basically, if you have a big loop, for example, if it iterates 100,000 times, you don't mispredict the branch much, right? If you basically loops usually iterate, as a result, they're taken. They have taken branches, so you get better accuracy with always taken prediction. Okay, I already mentioned this basically. Backward branches are usually taken, and backward branches are usually loop branches. And backward branches are branches where target address is lower than the branch PC. Okay, that leads to backward taken, forward not taken prediction. It's a form of static prediction also. And the basic idea is to predict the backward branches as taken, others as not taken. And the reason is people have found out that backward branches are loop branches and they're usually taken. Forward branches are non-loop branches and they're usually not taken, or at least there's not a lot of bias in the branches. As a result, treating these different branches separately is good. That leads to a better accuracy. And you will see this is also a static form of prediction because you don't make a dynamic decision based on the branch or program behavior, right? It's really whether the branch goes backwards in the code, the target address is earlier than the branch PC, or the target address is later than the branch PC in sequential code. Okay, this is fun, clearly. You can make this more interesting now by putting the compiler to work or the programmer to work. You can make it profile-based. Compiler determines the likely direction for each branch using a profile run and encodes that direction as a hint bit in the branch instruction format. So basically, branch instruction format has a hint bit, 1 bit, saying whether this branch is deemed by the compiler to be likely taken or not taken. Okay, and use that bit to guide the prediction. Okay, so this is nice because if the compiler says, oh, this branch is almost always taken, it sets the bit to be taken. If the compiler figures out some other way using input set, of course, it will set the bit to be not taken. Of course, this requires executing the branch once so that you see the branch target address as well as that bit, right? But later executions, you can use this profile-based prediction. So the upside of this is it gives you a per branch prediction, right? So the previous prediction mechanisms, always not taken, always taken, backward taken, forward not taken, are really per classes of branches or all branches, right? All branches are treated similarly. Here, you can distinguish between per branch. So it's more accurate than schemes in previous slide. Of course, this is true if the profile is representative. It's always true if the profile is representative, right? The downside is now your ISA requires hint bits in the branch instruction format. And accuracy also depends on dynamic branch behavior. So if the branches are biased, this is great. But if the branches are not biased, if it looks like this, so this is basically, I think, 20 iterations of a branch and which direction the branch went. 10 times it went taken, 10 times it went not taken. The compiler has only 1 bit. It can say taken or not taken. Either way, you get 50% accuracy. If the branch behaves like this, taken, not taken, taken, not taken, taken, not taken, in an interleaved manner, in 10 iterations versus 10 iterations taken and 10 iterations not taken, you still get 50% accuracy. So the compiler cannot identify, do well, at least with these non-biased branches. And as a result, your accuracy tanks. But you can see that these actually are quite predictable, right? If you were a little bit smart, these patterns are guessable, if you will, if you recorded the information in hardware, and we'll see that. So the accuracy also depends on the representativeness of the input set, profile input set, and we discussed this with any profile-based mechanism. If the compiler made a wrong decision, then actually the static branch prediction may become really bad, because the compiler may say the branch is taken, so predicted taken, but 100% of the time the branch becomes not taken at dynamic execution time because the input set is different. Then you have a problem, of course, right? Then this optimization becomes worse in terms of performance. Even a simple not taken prediction would have done better. Okay, there's another approach to static branch prediction. It's called program-based prediction or program analysis-based prediction. It's actually discussed in this beautiful paper, Branch Prediction for Free paper. And the idea here is to use heuristics based on program analysis, analyzing the program, not necessarily profile analysis, but analyzing the program and the dependencies and the type of branch instructions to determine a statically predicted direction by the compiler. So for example, there are many heuristics this paper proposes, but one heuristic is predict branch less than or equal to 0 as not taken. Essentially, these authors justify this by saying, usually these branches are not taken because negative integers are used as error values in many programs, and branch less than or equal to 0 opcodes are used to avoid those error values. So they're usually not taken. And this is reasonable. They analyze a bunch of programs. I don't know if this still holds, because you can see that this paper is almost 30 years old. Another heuristic, predict a branch guarding a loop execution as taken. Basically, usually if there's a branch that's guarding the loop execution, if condition is true, execute the loop. Otherwise, don't execute the loop. Then predict the branch such that you will execute the loop, meaning taken. This is because those guard branches are usually, again, protecting against some error values, for example, or boundary conditions, which don't happen as often. Again, these are heuristics, as you can see. They're not rules. Pointer and FP comparisons, if you're comparing two pointers, if you're comparing a pointer to null, for example, predict that it's not going to be equal to null, because again, that's a boundary condition potentially, or an error condition. Floating point comparisons, again, usually your floating point comparisons are not going to match. So basically, these are heuristics, some example heuristics, which make sense, I think, but they don't require profiling. That's the big upside here. But heuristics may not be representative or good. Also, that's a downside, as you can see, and requires compiler analysis and ISA support. True for other static methods as well. So these folks show that you get 20% branch misprediction rate as early as 27, 28 years ago. I don't know of any compiler that really employs all of these. They usually do profile-based, but some may, at a limited manner, can employ this. Okay, let me cover some of these static methods, and we're going to finish the lecture. But the last one, you can basically do everything that we discussed at the programmer level, right? Compiler may do it, either profile-based or heuristic-based, but as a programmer, you can do it also, right? You know your code, you can profile your code, or you can look at your code, you can guess based on the structure, semantic structure of your code, you can say, oh, this branch is going to be likely not taken or likely taken. So basically, the idea is programmer provides a statically predicted direction, sets that bit, hint bit in the ISA. And you can do it in the programming language by using pragmas that qualify a branch as likely taken versus likely not taken. Right? This is called a pragma. I'm going to introduce it in a little bit. But of course, if you're doing it at the programmer level, it doesn't require at least compile time profiling or program analysis, or the programmer needs to do something about it, right? But at least compiler doesn't get complicated in this case. And programmer, the big advantage of this is that as a programmer, you may know some branches and their semantics, their reasons, and their program behavior better than other analysis techniques. That semantic information you have in your head as an expert programmer usually, which the compiler cannot easily figure out, and certainly other hardware or heuristics may not be able to figure out. So that's the big advantage. Of course, the downside is now you require support from the programmer, programming language, compiler, and the ISA as well, so that this gets communicated all the way down into hardware as a hint bit in the ISA. But of course, this will also burden the programmer, right? And it does burden the programmer. Okay, let me talk about pragmas, because this relies on pragmas. But basically, these are keywords that enable a programmer to convey hints to lower levels of the transformation hierarchy. And these are some example pragmas that people use in C to convey the direction of a branch. If likely X means you're likely going to take this branch and execute this code over here. If unlikely error means it's going to be unlikely to take the branch and execute the code that's protected by this if. That's the idea. I mean, this is very simple, hopefully. Many other hints and optimizations can be enabled with pragmas. For example, whether a loop can be parallelized. You may have seen OpenMP parallel pragma. This is directly from the OpenMP parallel programming description. This directive explicitly instructs the compiler to parallelize the chosen segment of the code. Here, if you look at the likely versus unlikely, you're explicitly instructing the compiler to add a hint bit saying this branch is likely taken and this branch is unlikely taken, right? That's the idea. So you need this sort of programming language support. Okay, so we're almost done with static branch prediction. Essentially, all previous techniques can be combined also. It's obvious again, right? Like everything else that we discussed, you can combine many different techniques. You can combine static branch prediction techniques also. The question is how, of course. And I'm going to necessarily leave you with that almost, with the questions on this slide, essentially. How would you combine them? So do you override the decision of the programmer? If you're a compiler, do you override the decision of the programmer? Who do you trust more, basically? That's a tough question, actually. What is the common disadvantage of all three techniques? Well, I've already given you the idea, basically. We've kind of discussed that, basically. If the behavior of the program changes at runtime, you cannot adapt to dynamic changes because you have a single hint bit saying this branch is likely taken or not taken. And that bit doesn't change during the execution, which means that you cannot adapt to dynamic changes in branch behavior during runtime. And this can be mitigated by a dynamic compiler, like a just-in-time compiler. And just-in-time compiler, once in a while, recompiles the program and changes those hint bits, for example. But if you do it at a very fine granularity, the dynamic compiler will have a lot of overheads. And branches change behavior at a very fine granularity, as we will see later on. So what is a dynamic compiler? We've discussed this briefly, actually. It's a JIT, just-in-time compiler, a compiler that generates code at runtime. Like Java just-in-time compiler, Microsoft Common Language Runtime are examples, but there are new examples also that exist. So certainly these static techniques, every static technique can be made better. Code generation, instruction scheduling, branch prediction by using dynamic compilers. But dynamic compilers always have overhead, especially if you want to change the code frequently and at fine granularity. Okay, so this is where I'll stop. We've covered compile time, static branch prediction, which is clearly very interesting, but not enough. So in the next lecture, we're going to start with runtime branch prediction, and we're going to see very, very interesting techniques, including machine learning techniques to improve branch prediction accuracy, and also other human-designed heuristics to improve accuracy. And modern processors actually employ combinations of these different techniques, as we will also see. So at this point, I'm going to stop. I don't think I missed any questions, but if there are any questions, any burning questions, let me know right now. Otherwise, we're going to stop. And I wish you a nice weekend. Stay safe. And I will see you next week so that we can pick up from these really exciting algorithms to cover dynamic branch prediction.